The universe is a vast and mysterious place filled with wonders that have captivated human imagination for centuries. We've gazed at the stars for millennia, seeking answers to fundamental questions about our existence. From ancient civilizations mapping the stars to modern astronomers using advanced telescopes, our quest to understand the cosmos has been relentless. Where did we come from? This question has echoed through the ages, driving us to explore not just the heavens, but also the very essence of life itself. What are we made of? At the core of this inquiry lies the study of the building blocks of matter, from the complex structures of DNA to the fundamental particles that make up the periodic table of elements. How does it all work? The intricate dance of particles and forces governed by the laws of physics is a puzzle that scientists have been piecing together for generations. Two powerful tools in our quest for understanding are quantum mechanics and the study of space. These disciplines, though seemingly distinct, offer complementary insights into the nature of reality. These fields may seem unrelated, but they are deeply intertwined. Quantum mechanics, with its focus on the smallest scales, and astrophysics, with its exploration of the vast cosmos, together paint a comprehensive picture of the universe. They offer us a glimpse into the fundamental nature of reality itself. Quantum entanglement, for instance, challenges our understanding of space and time, suggesting that particles can be connected across vast distances instantaneously. Quantum mechanics is the strange and counterintuitive theory that governs the microscopic world of atoms and subatomic particles. It reveals a reality where particles can exist in multiple states at once, and where the act of observation can alter outcomes. It reveals a reality far different from our everyday experiences. Quantum computers, for example, harness these principles to perform calculations at speeds unimaginable with classical computers. Space, on the other hand, is the boundless expanse that holds galaxies, stars, and planets. It is a realm of unimaginable scale and beauty, where the laws of physics as we know them are put to the ultimate test. It is the grand stage on which the cosmic drama unfolds. From the birth of stars in nebulae to the collision of galaxies, space is a dynamic and ever-changing environment. Together, quantum mechanics and space exploration provide a more complete picture of the universe. They allow us to bridge the gap between the very small and the very large, offering insights that neither field could achieve alone. They allow us to explore the universe's smallest constituents and its largest structures. Particle collisions and accelerators reveal the fundamental forces at play, while telescopic observations uncover the vast architecture of the cosmos. This journey takes us to the very edge of human knowledge, where the familiar laws of physics break down and the universe reveals its most profound secrets. Black holes, for instance, challenge our understanding of gravity and space-time, offering a glimpse into the mysteries that lie beyond our current scientific grasp. As we continue to explore these frontiers, we are reminded of the boundless curiosity and ingenuity that drive human progress. Each discovery, whether in the realm of the quantum or the cosmic, brings us one step closer to unraveling the mysteries of the universe. The journey is far from over. With each new breakthrough, we deepen our understanding of the universe and our place within it. The quest for knowledge is a never-ending adventure, one that continues to inspire and challenge us. Quantum mechanics and the study of space are not just scientific endeavors. They are a testament to the human spirit's unyielding desire to explore, understand, and marvel at the wonders of the universe. Imagine you're at the bowling alley, but instead of a predictable game, you're playing quantum bowling. In this game, the bowling ball doesn't follow a straight path. It doesn't even exist in a definite location until it hits the pins. Instead, the ball exists as a wave of probability spread out across the entire lane. It's like the ball is everywhere and nowhere at the same time. This strange behavior is the essence of quantum mechanics. In the quantum world, particles like electrons don't behave like tiny billiard balls. They act more like waves, their location and momentum described by probabilities rather than certainties. It's a completely different set of rules from the classical physics we're so used to. The world we experience daily seems to follow predictable rules. These rules have been studied and understood for centuries, forming the foundation of what we call classical physics. A ball thrown in the air follows a defined arc, a path that can be precisely calculated using Newton's laws of motion. A dropped apple falls to the ground, a phenomenon famously described by Isaac Newton's law of universal gravitation. This is the realm of classical physics where objects have definite positions and speeds. The motion of gears and the swing of a pendulum can be predicted with great accuracy. We can predict their behavior with remarkable accuracy, using mathematical equations and computer simulations to model their trajectories and interactions. However, this predictable world breaks down at the atomic level. When we delve into the realm of the very small, the rules of classical physics no longer apply. In the quantum realm, things are fuzzy and uncertain. Particles do not have definite positions or speeds until they are measured. Particles can be in multiple states at once, a phenomenon known as superposition. The famous double-slit experiment demonstrates this, showing that particles can behave like waves, creating interference patterns. They can tunnel through walls, appearing on the other side of barriers that would be insurmountable in the classical world. This is known as quantum tunneling. They can even be entangled, their fates intertwined, regardless of distance. This means that a change in one particle can instantaneously affect another, no matter how far apart they are. This phenomenon is called quantum entanglement. Think of a coin spinning in the air. In the classical world, we know that it will eventually land as either heads or tails. In the classical world, the coin is either heads or tails, even if we don't know which until it lands. The outcome is determined, just unknown to us until we observe it. In the quantum world, the coin is both heads and tails simultaneously, until we observe it. This is because in the quantum realm, particles exist in a state of superposition, holding multiple possibilities at once. This mind-bending concept is called superposition. It challenges our understanding of reality and forces us to rethink the nature of existence itself. The quantum world is a place of endless possibilities where the rules of classical physics no longer apply, and the boundaries of what we know are constantly being pushed. Light is one of the most fascinating phenomena in the universe. It has intrigued scientists and philosophers for centuries, leading to numerous theories and experiments to understand its true nature. It allows us to see the world around us and carries information across vast cosmic distances. From the twinkling stars in the night sky to the vibrant colors of the sunset, light is essential to our perception of the universe. But what exactly is light? This question has puzzled humanity for ages. Is it a wave like the ripples on a pond, or is it a stream of particles like tiny bullets? Is it a wave or a stream of particles? This fundamental question has led to groundbreaking discoveries in the field of physics. The answer, surprisingly, is both. Light exhibits properties of both waves and particles, a concept that seems counterintuitive, but is supported by extensive scientific evidence. Light exhibits a dual nature, behaving like a wave in some experiments and like particles in others. One of the most famous experiments demonstrating this is the double-slit experiment. This is known as wave-particle duality. In the double-slit experiment, light creates an interference pattern characteristic of waves when not observed, but acts like particles when measured. It's like a chameleon that can change its appearance depending on the situation. This adaptability of light is a cornerstone of quantum mechanics. When light passes through a prism, it spreads out into a spectrum of colors, just like waves in water. This phenomenon, known as dispersion, beautifully illustrates light's wave-like nature. This is light's wave-like nature on display. The spreading of light into its constituent colors is a direct consequence of its wave properties. But light can also act like a stream of tiny energy packets called photons. These photons are the particle aspect of light, each carrying a discrete amount of energy. This is evident in the photoelectric effect, where light shining on a metal surface knocks electrons loose, like a rain of particles striking the surface. This effect was crucial in the development of quantum theory and earned Albert Einstein a Nobel Prize. Einstein's explanation of the photoelectric effect provided strong evidence for the particle nature of light, showing that light can be thought of as quanta, or packets of energy. Today, our understanding of light's dual nature is fundamental to many technologies, from lasers and fiber optics to solar panels and quantum computing. The wave-particle duality of light continues to inspire and challenge scientists, driving innovation and expanding our knowledge of the universe. As we continue to explore the mysteries of light, we uncover more about the cosmos and our place within it. Light, in all its forms, remains a beacon of discovery and wonder.
Space. It's a word that sparks curiosity and awe, igniting our imagination and sense of adventure. When we look up at the night sky, we see just a tiny glimpse of the vastness that surrounds our planet, a mere fraction of the cosmic expanse. Space is everything that is not on Earth, an infinite realm beyond our terrestrial home. It's the airless void where planets, stars, and galaxies reside, a silent stage for celestial wonders. It's a place of incredible beauty and mind-boggling mystery, where the laws of physics stretch our understanding. Imagine a dark, endless ocean, dotted with islands of light, each one a galaxy teeming with stars. That's a bit like space, with galaxies like our own Milky Way scattered throughout, each a universe in its own right. In this vast expanse, we find wonders that challenge our understanding of the universe, pushing the boundaries of science. Black holes warp time and space, creating gravitational fields so intense that not even light can escape. The quantum vacuum hums with hidden energy, a sea of potential waiting to be discovered. We are just beginning to explore the universe, taking our first steps into the cosmic ocean. With telescopes like Hubble, we peer deeper into the cosmos, unveiling secrets of distant stars and galaxies. We send probes to distant planets, searching for clues about our solar system's past and the potential for life beyond Earth. Every new discovery brings more questions than answers, fueling our quest for knowledge. But that's the beauty of space exploration, the endless pursuit of understanding. It's a journey into the unknown, a quest to understand our place in the grand scheme of things and to uncover the mysteries of the universe. Imagine a trampoline. This trampoline isn't for jumping, though. It represents something called SpaceTime. SpaceTime is the fabric of our universe, a combination of space and time that's woven together. Now, picture placing a bowling ball in the middle of the trampoline. What happens? The ball makes the trampoline sag, right? That's similar to how massive objects like planets and stars warp space-time. This warping is what we experience as gravity. The Earth orbits the Sun because the Sun's massive size creates a kind of dip in space-time, and Earth rolls around in that dip, like a marble circling a bowling ball. The more massive an object, the more it warps space-time, and the stronger its gravitational pull. It's a pretty amazing concept, isn't it? Here's another mind-bending idea. The universe is expanding. Imagine a balloon with dots drawn all over it. Now, blow up the balloon. What happens to the dots? They all move farther apart, right? That's what's happening to galaxies in our universe. Space itself is stretching, pushing galaxies away from each other. The farther away a galaxy is from us, the faster it appears to be moving away. This expansion means the universe was once much smaller and denser than it is today. It all started with a big bang, an unimaginably powerful burst of energy that set everything in motion. The universe is still expanding today, and we're not exactly sure how big it will get or if it will ever stop expanding. It's a mystery that scientists are working hard to solve. Black holes are some of the most extreme objects in the universe. Imagine a whirlpool, but instead of water, it's gravity that's pulling everything inward. That's kind of what a black hole is like. Black holes form when massive stars collapse at the end of their lives. Their gravity becomes so strong that nothing, not even light, can escape their grasp. If you got too close to a black hole, the gravity would be so intense that it would stretch you out like spaghetti. This is called spaghettification, and it's a real thing. Black holes are mysterious and fascinating objects. They teach us about the limits of gravity and the nature of space and time itself. Section 5. The quantum vacuum. A sea of potential. Even in the emptiest regions of space, where there seem to be no stars or planets, there's actually a lot going on. It might look like a vast, silent void, but it's far from empty. Imagine the calm surface of the ocean. It appears tranquil and undisturbed. It might look peaceful, but beneath the surface there's constant motion from waves and currents. The ocean is teeming with life and activity, hidden from plain sight. That's a bit like the quantum vacuum. It seems empty, but it's actually full of dynamic processes. It's not really empty, but filled with tiny particles that pop in and out of existence. These particles are incredibly small and fleeting. These particles are like tiny ripples of energy, constantly appearing and disappearing. They create a continuous dance of creation and annihilation. This constant activity means that the quantum vacuum is full of potential energy. It's a sea of possibilities, brimming with untapped power. Scientists believe that this energy could be harnessed one day, providing us with a new source of power. This could revolutionize our understanding of energy and its applications. The quantum vacuum is a strange and wonderful place, and it reminds us that even in the seemingly emptiest regions of space, there's always something happening on a microscopic level. It's a reminder of the hidden complexities of our universe. Section 6. The cosmic dance of stars and galaxies. Space is not just an empty void. It's alive with the cosmic dance of stars and galaxies. Stars are giant balls of hot gas that emit light and heat. They are born in clouds of gas and dust, live for millions or billions of years, and eventually die, sometimes in spectacular explosions called supernovas. Galaxies are vast collections of stars, gas, dust, and dark matter, all held together by gravity. Our own Milky Way galaxy is a barred spiral galaxy, a majestic swirl of billions of stars. These celestial objects move and interact in complex ways, driven by gravity and other forces. Their interactions create stunning nebulae, star clusters, and other cosmic wonders that we can observe from Earth. Section 7. Searching for life beyond Earth. One of the most profound questions we ask ourselves is, are we alone in the universe? The search for extraterrestrial life, or aliens, has captivated our imaginations for centuries. Scientists are searching for signs of life on other planets and moons within our solar system and beyond. They look for evidence of water, organic molecules, and other conditions that could support life as we know it. While we haven't found definitive proof of alien life yet, the vastness of the universe suggests that it's highly unlikely that we are alone. The search continues, fueled by curiosity and the hope of one day making contact with another intelligent civilization. Section 8. Unraveling the mysteries of the cosmos. Space exploration is not just about satisfying our curiosity. It's about pushing the boundaries of human knowledge and understanding our place in the universe. By studying space, we gain insights into physics, chemistry, biology, and other fields of science. We develop new technologies that benefit us here on Earth, from satellite communication and GPS navigation to medical imaging and material science. Space exploration inspires innovation and encourages us to think beyond our terrestrial limits. The more we learn about space, the more we realize how much we still don't know. But that's part of what makes it so exciting. There are countless mysteries out there waiting to be solved, and each new discovery brings us closer to understanding the fundamental. Section 9. Our future among the stars. As we continue to explore space, we dream of a future where humanity becomes a multi-planetary species, living and thriving beyond Earth. We envision establishing colonies on Mars, mining asteroids for valuable resources, and creating sustainable habitats on other planets. Perhaps even venturing beyond our solar system to explore other star systems, seeking new frontiers and opportunities. The challenges of space travel are immense, requiring advanced technology and innovative solutions. But so are the potential rewards, which include new scientific discoveries and the survival of our species. By reaching for the stars, we challenge ourselves to overcome technological and scientific hurdles, fostering international collaboration and unity. We push the limits of human ingenuity, constantly innovating and adapting to new challenges. The future of space exploration is full of promise and wonder, offering endless possibilities for discovery. It's a future where we continue to unravel the mysteries of the cosmos, expanding our knowledge and horizons. We expand our understanding of the universe we call home, seeking answers to age-old questions. And who knows? Maybe one day, we'll even find evidence of other intelligent life out there, sharing this incredible journey of discovery with us. Together, we can achieve the extraordinary, exploring the vast unknown and making our mark among the stars.
Imagine a vast cosmic ocean, an endless expanse filled with mysteries and wonders beyond our comprehension. Two mighty ships set sail, each embarking on a journey to explore the depths of this cosmic ocean, seeking to uncover its secrets. One ship, named Relativity, sails smoothly across the open sea, its journey marked by elegance and precision. It navigates the gravitational waves, the swells and dips of space-time caused by massive objects like stars and galaxies, effortlessly gliding through the fabric of the universe. Relativity is Einstein's masterpiece, a theory that revolutionized our understanding of how gravity shapes the universe on the largest scales, bending light and warping time. The other ship, quantum mechanics, delves into the microscopic world where the rules of the game are entirely different. It explores the choppy waters of atoms and particles where uncertainty reigns and probabilities dictate outcomes. Here energy comes in tiny packets called quanta, and particles behave unpredictably like waves crashing on the shore, sometimes acting like particles, other times like waves. Quantum mechanics governs the realm of the very small, where the bizarre and the counterintuitive become the norm. Both ships are incredibly successful in their own right, each providing profound insights into their respective domains. But here's the catch. They seem incompatible, like two languages that cannot be translated into one another. Their rules, their very languages, clash when brought together, creating a paradox that has puzzled scientists for decades. This is the central problem in modern physics, the quest to unify these two giants into a single, coherent framework that can describe the universe at all scales. Some believe that string theory might be the answer, proposing that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. Others explore different avenues, from loop quantum gravity to various other theories, each offering a piece of the puzzle. The dream is to find a unified theory, a grand synthesis that can seamlessly merge the smooth, continuous world of relativity with the discrete, probabilistic world of quantum mechanics. Until then, the journey continues, with each ship charting its course through the vast, uncharted waters of the cosmos, driven by the human spirit of exploration and the quest for knowledge. Perhaps one day these two giants will sail together, their paths converging to reveal the ultimate truths of our universe. Until that day, we watch, we learn, and we dream of the possibilities that lie ahead in this grand cosmic voyage. This incompatibility creates a major headache for physicists. The challenge lies in the fact that the two most successful theories in physics, general relativity and quantum mechanics, don't play well together. General relativity, which describes the force of gravity and the large-scale structure of the universe, works perfectly for stars, galaxies, and the cosmos. On the other hand, quantum mechanics, which explains the behavior of particles at the smallest scales, is incredibly accurate for atoms and subatomic particles. But when we try to combine these two theories, especially in extreme conditions like black holes or the Big Bang, they clash. We need a new theory, a grand unification, to reconcile these two giants. This elusive theory, often referred to as the theory of everything, aims to merge the principles of general relativity and quantum mechanics into a single, coherent framework. Such a theory would not only deepen our understanding of the universe, but also unlock new realms of physics, potentially leading to groundbreaking technologies and insights. This is where quantum gravity comes in. Quantum gravity is an area of theoretical physics that seeks to describe gravity according to the principles of quantum mechanics. It attempts to explain how gravity works at the smallest scales, where the effects of quantum mechanics cannot be ignored. By doing so, it hopes to bridge the gap between the macroscopic world of general relativity and the microscopic world of quantum mechanics. Think of a black hole, a place where gravity is extremely strong, squeezing matter into an infinitely small point. In these extreme environments, the effects of both general relativity and quantum mechanics are significant. Understanding what happens inside a black hole requires a theory that can handle both the immense gravitational forces and the quantum effects at play. To understand what happens at the heart of a black hole, we need both gravity and quantum mechanics to work together. That's not all. Quantum gravity could also provide insights into other cosmic phenomena where these two forces intersect. For instance, it could help us understand the nature of singularities, the points of infinite density predicted by general relativity. Quantum gravity might also hold the key to the Big Bang, the birth of our universe. The Big Bang represents a singularity where the laws of physics as we know them break down. A successful theory of quantum gravity could explain the conditions of the early universe and how it evolved into the cosmos we observe today. It might even explain what dark matter and dark energy are, two mysterious phenomena that make up most of the universe, despite being invisible and undetectable by conventional means. Dark matter and dark energy exert a profound influence on the structure and expansion of the universe. A unified theory that includes quantum gravity could shed light on these enigmatic components, revealing their true nature and role in the cosmos. One attempt to unify these forces is string theory. Imagine the universe as a grand symphony. In classical physics, the universe is like an orchestra with each instrument playing a distinct note. But in string theory, the universe is more like a single string instrument, a cosmic violin. The different vibrations of this string produce the different particles and forces we observe. Just like different notes combine to create a melody, different string vibrations create the symphony of the cosmos. Another contender is loop quantum gravity. Instead of smooth space-time, imagine space-time as a fabric woven from tiny, indivisible loops. These loops are like pixels on a computer screen, representing the smallest possible units of space and time. Just like you can't have half a pixel, you can't have less than one loop of space-time. In loop quantum gravity, space-time itself becomes granular, quantized at the Planck scale, which is incredibly small. Section 5, the search continues. Experiments and observations. Both string theory and loop quantum gravity are incredibly complex and still under development. These theories aim to unify the fundamental forces of nature, but they are still in the theoretical stage. String theory suggests that the fundamental particles are not point-like dots, but rather tiny vibrating strings. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, proposing that space is made up of tiny, discrete loops. Physicists are hard at work using mathematical equations and computer simulations to test their predictions. They spend countless hours developing models and running simulations to see if their theories hold up under various conditions. These simulations require immense computational power and sophisticated algorithms to handle the complex mathematics involved. But here's the challenge. These theories operate at energy levels far beyond what we can create in our most powerful particle accelerators. The Large Hadron Collider, for example, can reach energies of up to 13 tera-electron volts. But the energies required to test these theories directly are many orders of magnitude higher. This makes it incredibly difficult to gather experimental evidence to support or refute these theories. So how do we test them? This is one of the biggest questions facing physicists today. They are constantly brainstorming and coming up with innovative ways to test these theories indirectly. One approach is to look for subtle effects that these theories might have on observable phenomena. Scientists are searching for subtle effects of quantum gravity in the cosmos, such as tiny variations in the cosmic microwave background radiation, the afterglow of the Big Bang. These variations could provide clues about the nature of quantum gravity and help us understand the early universe. By studying the cosmic microwave background in great detail, scientists hope to uncover evidence that could support or challenge these theories. They are also looking for ways to simulate these extreme conditions in the lab using ultra-cold atoms and powerful lasers. By cooling atoms to near absolute zero and using lasers to manipulate them, scientists can create conditions that mimic the high-energy environments where these theories might be tested. These experiments are incredibly challenging and require precise control over the experimental conditions, but they offer a promising avenue for testing these groundbreaking theories. Section 6. The implications of quantum gravity. Finding a theory of quantum gravity would be a monumental achievement, revolutionizing our understanding of the universe. It would be like discovering a new continent, a new realm of physics with unimaginable possibilities. Imagine harnessing the power of quantum gravity to create new technologies, perhaps even warp drives for faster-than-light travel. Or imagine understanding the true nature of black holes and the Big Bang, unlocking the secrets of the universe's birth and ultimate fate. Section 7. Beyond the Horizon Unification and the Future of Physics. The quest for quantum gravity is not just about finding a single equation, it's about our deep desire to understand the universe at its most fundamental level. It's about unifying all the forces of nature into a single elegant framework. This quest has driven physics forward for centuries, leading to countless discoveries and technological advancements. And it will continue to inspire generations of physicists to come. Section 8. Our place in the quantum universe. As we delve deeper into the quantum realm, we begin to question our very place in the universe. If space-time is granular, does that mean our reality is pixelated too? Does the act of observation influence the quantum world? These are profound questions that challenge our perception of reality, but they also remind us of the beauty and mystery of the universe we inhabit. Section 9. A final thought, the never-ending quest. The search for quantum gravity is a journey into the unknown. It's a journey driven by curiosity, creativity, and a deep sense of wonder. It's a journey that may never truly end, but each step we take brings us closer to understanding the universe and our place within it.
Space and time. These two concepts have fascinated humanity for millennia, sparking curiosity and wonder. They are the very fabric of our existence, the stage upon which the drama of the universe unfolds. Everything we know, everything we are, exists within this grand cosmic stage. From the smallest particles to the largest galaxies, all are bound by the laws of space and time. But what are space and time really? How do they work? These questions have puzzled scientists and philosophers alike for centuries. And what is the role of the strange world of quantum mechanics in all of this? This realm, where particles can exist in multiple states at once, challenges our very understanding of reality. For centuries, we thought we knew. We believed we had a firm grasp on the nature of the universe. Space was the vast emptiness between stars and planets, a fixed and unchanging backdrop to the cosmic drama. It was the stage, and the celestial bodies were the actors. Time was a river, flowing steadily from past to future, carrying us all along with it. It was a constant, unyielding force that governed our lives. But then came the revolutions of the early 20th century. These groundbreaking discoveries would forever change our understanding of the universe. Albert Einstein, with his theories of relativity, shattered our Newtonian view of space and time, revealing them to be not separate entities, but interwoven aspects of a single fabric space-time. This was a radical shift in our perception of the cosmos. And then there was quantum mechanics, a theory even stranger still, which revealed that on the smallest scales, the universe behaves in ways that defy our everyday intuition. Particles can be in multiple places at once, and their behavior can only be described in terms of probabilities. These discoveries have opened up a universe of wonder, where the more we learn, the more questions arise. The cosmos is a vast, mysterious place, full of surprises and endless possibilities. As we continue to explore and understand this incredible universe, we are reminded of our own small place within it. Yet it is this very curiosity and drive to understand that makes us a part of the grand cosmic story. The journey of discovery is far from over. With each new breakthrough, we peel back another layer of the cosmic onion, revealing deeper truths about the nature of reality. The universe is a vast, wondrous place, and our quest to understand it is one of the greatest adventures of all time. Quantum mechanics is a branch of physics that studies the very, very small, the world of atoms and subatomic particles. It delves into the fundamental building blocks of matter, exploring the intricate and often bizarre behaviors that govern the microscopic realm. Unlike the macroscopic world we experience daily, the quantum world operates under a different set of rules, revealing a universe that is both fascinating and perplexing. And in this strange realm, the familiar rules of classical physics break down. Classical physics, which explains the motion of planets and the behavior of everyday objects, fails to describe the peculiarities observed at the quantum level. Here, particles can exist in multiple states at once, and their properties are not as straightforward as they seem. One of the key principles of quantum mechanics is wave-particle duality. This principle challenges our conventional understanding of particles and waves, suggesting that entities like electrons and photons exhibit both particle-like and wave-like characteristics, depending on how we observe them. This means that particles, like electrons and photons, can behave like both waves and particles. In experiments such as the famous double-slit experiment, particles create interference patterns typical of waves, yet they also impact detectors as discrete packets of energy, or quanta. Imagine a tiny ball that can also act like a ripple in a pond, and you start to get the idea. This duality is not just a theoretical concept, but a fundamental aspect of how nature operates at the smallest scales. Another important concept is the uncertainty principle, formulated by Werner Heisenberg. This principle is a cornerstone of quantum mechanics, highlighting the intrinsic limitations in our ability to measure certain pairs of properties simultaneously. This principle states that there are fundamental limits to what we can know about a particle's position and momentum at the same time. The more accurately we determine a particle's position, the less precisely we can know its momentum, and vice versa. The more precisely we know one, the less we can know about the other. This inherent uncertainty is not due to any flaws in our measurement tools, but is a fundamental characteristic of the quantum world itself. This is not a matter of our instruments being imprecise. It is a fundamental property of nature. Quantum mechanics forces us to rethink our understanding of reality, challenging our perceptions and opening up new possibilities for technology and scientific discovery. The quantum dance continues to intrigue and inspire, revealing a universe that is far more complex and mysterious than we ever imagined. For centuries, space was seen as the opposite of matter, the vast emptiness that separates stars and galaxies. It was thought to be a void, a nothingness that simply existed to provide a backdrop for the celestial bodies. But Einstein's theory of general relativity revolutionized our understanding of space, revealing it to be an active player in the cosmic drama. No longer was space just a passive stage. It became a dynamic entity that interacts with matter and energy. According to general relativity, gravity is not a force acting across empty space, but rather a curvature in the fabric of space-time itself. This was a groundbreaking shift from the Newtonian view of gravity as a force pulling objects towards one another. Massive objects, like stars and planets, warp the space-time around them. Much like a bowling ball placed on a trampoline curves the fabric. This warping effect is more pronounced with larger masses, creating deeper curves in the space-time fabric. This curvature of space-time is what we experience as gravity. It's the reason why planets orbit stars and why we stay grounded on Earth. The deeper the curve, the stronger the gravitational pull. Just like a marble rolling on the trampoline would be deflected by the bowling ball's indentation, objects moving through space-time are deflected by the curvature caused by massive objects. This deflection is what keeps planets in their orbits and governs the motion of galaxies. The interplay between matter and the fabric of space-time is a dance that shapes the universe. So, we have quantum mechanics, which describes the bizarre behavior of matter on the smallest scales, and general relativity, which explains the large-scale structure of the universe and the nature of gravity. But here's the rub. These two pillars of modern physics don't quite play well together. One of the biggest challenges in modern physics is to find a way to unify these two theories into a single, coherent framework, a theory of everything. And this is where our exploration of the universe takes us to the very edge of our current understanding. Section 5. The Expanding Universe. One of the most profound discoveries of the 20th century was that our universe is not static, but is, in fact, expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This discovery, based on the observations of Edwin Hubble, implies that the universe had a beginning, a moment in time when everything was compressed into an incredibly hot, dense state known as the Big Bang. Section 6. The Quantum Foam. Now let's zoom in to the smallest possible scales of the universe, to a realm where quantum mechanics reigns supreme. Here, according to some theories, space-time itself is not smooth and continuous, but is instead a seething, bubbling froth known as quantum foam. Imagine the fabric of space-time as a churning ocean, with virtual particles constantly popping in and out of existence, like tiny fleeting bubbles. This quantum foam is a consequence of the uncertainty principle, which allows for the temporary creation and annihilation of particles and antiparticles. Section 7. The Future of Exploration. The quest to understand quantum mechanics and its relationship to space-time is a journey into the unknown. It is a journey that will likely challenge our most fundamental assumptions about the nature of reality. But this is the beauty of science. It is a process of constant exploration, of questioning what we think we know and pushing the boundaries of our understanding. And as we delve deeper into the mysteries of the cosmos, we are sure to make discoveries that will amaze and inspire us. Section 8. The Universe in Your Hand. The universe is vast and awe-inspiring, but it is also within us and all around us. Every atom in our bodies was once forged in the heart of a star, and the molecules that make up our DNA bear the imprint of cosmic events that unfolded billions of years ago. So the next time you look up at the night sky, remember that you are not just an observer of the cosmos, but an integral part of it. The universe is not something distant and separate from us. It is the very fabric of our being. Section 9. Keep looking up. The universe is full of wonders, and we are only just beginning to unravel its mysteries. So keep asking questions, keep exploring, and never lose your sense of wonder. For in the words of the great Carl Sagan, somewhere, something incredible is waiting to be known.